Well, hello everyone, and welcome to my webinar titled Optimization for Engineering Applications with Maple and MapleSim. My name is Sam Dow, and I am an application engineer at Maplesoft. So as the title says, today we're going to learn how to use Maple optimization toolboxes to the optimization to find the optimal solution for the virtual models that we built in MapleSim, physical modeling software. So optimization in general is a process of finding the best answer to a given problem automatically using some search technique. The diagram here shows a general design process. Start with a model with the initial design. You then simulate to see how the virtual model behaves. Often the system doesn't satisfy with the first try, so you're going to have to come up with another set of parameters and try again. So the process is repeated until we find the optimal design by satisfying an objective function, which is subject to some constraint conditions as well. In Maple, there are two separate optimization toolboxes. The local optimization toolbox, which uses local search algorithms to find the optimal solution. These local search methods work best for problems which only have one single optimum. The second toolbox is the global optimization toolbox, which finds the best solution in the presence of multiple local optima. So the main difference between the global optimization toolbox from the local optimization toolbox is that the global optimization toolbox algorithms do not rely on an initial point, but it requires finite bounds for all the design parameters in order to limit search space. So due to the limited time frame of the webinar today, I'm not going to be able to give you the details about the algorithms used in these two optimization toolboxes. But in order to find the information, the detailed information about this, the algorithms being used in these toolboxes, you can use the Maple search, Maple help window to get further details about the algorithms being used in these two toolboxes. For example, in order to find the information about the local optimization toolbox, you can simply type optimization in a search window in the help, and then hit enter. And in a few seconds, Maple will show you the details about the local optimization toolbox, which basically is a collection of commands for solving optimization problems. So you can see that this is a list of the commands in the local optimization toolbox in Maple. For example, we can see that we have the linear programming solver, we have the least square solver, quadratic problem solver, nonlinear programming solver as well. In order to get details about the global optimization toolbox algorithm, you can type global optimization in the search window in Maple help and hit enter again, and that will give you the details about the global optimization toolbox in Maple as well. So in order to learn further about the differences between these two toolboxes in Maple, let's go through a simple example in Maple. And what I'm going to be doing now, I'm going to be using the interactive command in the global optimization toolbox in Maple in order to compare the solutions that we can obtain for a simple function in Maple using the two optimization toolboxes. So I'm typing in optimization interactive. And hit enter. And the examples that I'm going to be using is this is a very simple example. I'm going to click on edit and type in the functions that I want to get the optimal solution for. And the function that I'm going to be using is going to be I'm going to be typing in the functions that I want to find the optimal solution for. X minus x square minus y to the power 5 times exponential function minus x square minus y square. So hopefully I didn't make any typo. Okay, so now I do have the functions that I want to get the optimal solution. So I also need to define the boundary for the design for the two design parameters x and y as well. In order to do that, I click on constraints and bounds on the edit button next to constraints and bound, and this will allow me to define the bounds for the two parameters x and y. And I want x to be between -2 and 2. Hit add. And for y, I will also want the same thing for y, which is between -2 and 2. I hit add again, and we're done when I'm done with that. So so now let's plot the function and see how it looks like. Choose now. I must solve it first. So I'm going to be plotting the function and see how the function looks like. So this is a function that I want to find the minimum or the maximum point for. So you could clearly see that this function has several local optima, namely the maxima and the minima. For example, you can see that it has 3 or 4 different maximas and the same number of minima as well. And let's say if you want to find the maximum point of the function, and I just select maximum, the maximize. And for the local search algorithms to start, we also need to define the initial guesses at the starting point for the search algorithms to start with. Let's say if we want to, so without the knowledge of the maximum point of the function, I'm going to randomly define the initial points. Let's say x equal to 1 and y equal to -1, which is the starting points that I want the search algorithm to start at. And if I hit the solve button again, you can see that the objective function value has been printed out. And if I hit the plot button, and in the graph, you're gonna see that the maximum point is located at x equal to 2 and y equal to -2. Let me see. So which is this? So this is the maximum point that the local search algorithm found, which is clearly not the true maximum point of the function. This is just a local maxima. So if I change the initial search point again, let's say x equal to 0 and y equal to 0, I want this, the search algorithm to start at the point 0, 0, and I click on the solve button again. So I come up with another objective function, which is 10.0678. So if I click on the plot button again and take a look into the function, you can see that this is the true maximum point of the function. So you can see that the local search algorithm heavily dependent on the initial starting point. So on the other hand, if instead of using the local search algorithm, I select the global solver and then define some initial point. I don't really need to define the initial point for the global solver, and I can just click on the clear button to wipe out all the initial values for the variables, and I hit the solve button again, and I will come up with the same solution as the final as the last results that we can obtain with the local search algorithm. So you can see that the value of the object function now is 10.0678, and if you can see that on the plot window as well, so which is a grid point at the top here. So now let's come back to our slides. So for the rest of the presentation today, we're going to learn how to use Maple's Global Optimization Toolboxes to find the optimal solutions for the physical models built in MapleSim. So what is MapleSim? MapleSim is a physical modeling tool developed for modeling and simulating physical systems. You can think about an electrical network, automotive systems, hydraulic pumps. So all of this kind of system can be modeled very easily in MapleSim. So how can MapleSim help with the optimization process? So the way MapleSim help with the optimization process is that MapleSim can produce high performance models of physical system with very little effort. For example, you can easily build a physical system with a great complexity of an electrical network or a mechanical system in MapleSim in a very short amount of time. And MapleSim also can generate the optimized code for the optimization processes as well, and the code being generated by MapleSim are highly optimized, which allows the code to be executed in very short time. So this is very important for any optimization process, because optimization process usually requires a very fast model in order to put that in an optimizer that can run thousands or hundreds of thousands of iterations. And to further speed up the simulation or the calculation, MapleSim also has a very robust numerical solver that can handle very complex model equations. So in order to understand how we can use Maple Optimization Toolboxes to do optimization of models in MapleSim, let's start with a very simple example. So the example that we start with today is the problem of using a tuned mass damper to reduce the steady state vibration of a long span cantilever and composite floor. So as you can see in the picture here, the floor is modeled as a cantilever beam spanning between the floor and the ring girders. So every time a dance event happens, the movements from the dance exert a periodic excitation force on the floor, which happens to coincide with the first natural frequency of the floor, and causing the floor to vibrate at very high amplitude. So the solution here is to install a mass damper system which can be tuned to each resonant frequency of the floor in order to reduce the vibration. So the systems that we're going to be setting up in MapleSim is can be represented by the schematic diagram on the right hand side. So now let's go into MapleSim and see how that works. So to optimization, so to solve this optimization problem, I have developed a virtual model of the dance floor with a tuned mass damper system in MapleSim. So what you see on the screen right now is the MapleSim interface. So you can see that the first mass that I'm selecting now is actually the floor, and on the right hand side you can see that this is a parameter for the mass, which is corresponding to the mass of the cantilever beam for the composite floor. And and you can see that the floor is supported by a linear spring and damper. And all of these parameters can be measured and entered into this virtual model in MapleSim. And the dance floor is excited by an external force, which has amplitude of 7500, so we can actually put any number in here. And the most important parameter for the excitation force is the frequency of the vibration, which is calculated based on the mass and the stiffness of the cantilever beam. So the frequency is actually equal to the natural frequency of the system of the dance floor combined with the springs and damper. So if you and on top of that we have the mass, which is corresponding to the mass of the tuned damper system, and the mass is attached to the floor, which shows that the tuned mass damper system sits on the tip of the cantilever beam and is connected to the composite floor through another spring and damper, whose parameter we need to identify. So the parameter of the tuned mass damper systems is parameterized by the two parameters C pi and D pi, and we need to identify these two parameters so that we can minimize the vibration of the dance floor. And I also put a sensor here to measure the displacement or the amplitude of the vibration of the dance floor mass. So if you simulate this, if you run the simulation in MapleSim now, you're gonna see that the resonance effect of the excitation force and the natural frequency of the system causes the dance floor to vibrate at a very high frequency and high amplitude. So we need to reduce this. So how can we solve this the optimization problem using the Maple Optimization Toolbox? In order to do that, we first need to create a Maple worksheet that allows us to use the Maple optimization commands to solve this optimization problem, or to determine the two parameters C pi and D pi, so that the vibration is reduced. So in order to do that, we go to a dialog box called create attachment, and we go all the way to the end and click on the worksheet, which will generate a blank worksheet for us. So from here, you can select the subsystem for the dance floor combined with the untuned mass and damper system. So the first command has been created for us is a MapleSim API command called link model, which allows us to link a variable A to the MapleSim model that we selected. So I would like to load up a helpful package called linear algebra, because I need to use some command from this package in order to do some post-processing on the simulation result. I'll execute this first, and I will execute this link model command. So now I can access the API command within the MapleSim package through the variable A. For example, you can do a lot of things using the API commands. You can interact with the MapleSim model within Maple environment. For example, what you can do is you can call the command get parameter with option all parameters, which allows you to extract all the parameters from the model. Okay, so you can see that this is a list of parameters that we can see from the MapleSim model. So what I want to do next is that I want to generate a C code for this MapleSim model. So this C code will allow me to execute the model simulation faster. So this C code has been optimized. So the reason why we need the C code is that because optimization processes usually requires us to run the simulation hundreds or even thousands of times. So having the optimized C code that has short execution time will help a lot with the optimization processes. And in order to generate the C code from the model, we gonna call the command called get compiled proc command. It is one of the API commands in the MapleSim package. So what this command does is that it will generate a C code or the optimized C code from the model and assign it to the variable that I defined called cproc. And I will also define the solver that I want to use as well. So the solver that I use is AK4 runs good 4, and I want to define the sampling rate. And two default parameter. That I want to optimize. That I want to identify. I'm giving these two parameters some default values. There we go. Okay, so the C code for the model has been generated. So in order to test the C code, you can run a sample simulation. For example, if I want to run a simulation by calling the cproc procedure and passing the two parameters, 1 in here, then I can run the simulation, and the results that I will get is a matrix. You can see the content of this matrix by double clicking on it. So the first column is the time, and the second column is the probes that I attached to the displacement sensor, which is corresponding to the amplitude of the vibration of the dance floor. So you can actually plot this very easily by calling the plot commands and passing the results data into the plot command, which will give us this plot. So this is the same plot that we can that you saw by running the MapleSim by running the simulation in MapleSim environment. So so the next step that we want to do is that we're gonna define an objective function that we want to minimize. So the objective function that we want to define, I'm going to define that through a Maple procedure, and I call the objective function obj, and there are two parameters that I want to pass into this procedure, C and D, which are the parameters that I want to find. I'm going to define a local variable result to store the results after the simulation. So to run the simulation, I simply called cproc and the durations of the simulation is 100 seconds. Okay, so those are all the parameters that I want to use, options that I want to use for the cproc command. And after the simulation is ran, the result will be stored in the variables called result. And I'm going to add up all the data points of the results in order to calculate the square error. I'm going to use add command in Maple, and I'm going to add up all the data points from because the results we're going to be obtaining is going to be a two-column matrix. So the first column is time column, the second column is the results, is actual simulation results of the amplitude of the vibration. So you want to you want to have the variable I that runs from the first row to the last row for the second column, and you want to square it as well. So I go from 1 to the dimension of the matrix, which is the size of the rows. Okay, so we have defined our objective function. So it's the objective function is, you can put a return command here to make it to improve the clarity of the code here. So what we return here is going to be the square error of all the data points for the results, or the amplitude of the vibration. So now we are going to call the optimization package using the nonlinear programming solve command to find the optimal solution for this problem. So we're going to pass the objective function obj into this. So this is how we're going to specify the parameter for the objective function. So we're going to pass the parameter c and d into this as well. The methods that we're going to be using is I'm going to use the nonlinear simplex method. I also want to define an evaluation point limit, so that it does not stop prematurely. I put it very high. Okay, so all I need to do now is just simply to execute this command in order to run the computation. So I will leave it to Maple to find the optimal solution for me. Okay, so now we have obtained the optimal solution to this problem. And the two optimal parameters that Maple Optimization Toolbox has found is the spring constant is 1.03 times 10 to the power of 6, and the damping coefficient is 166. So let's see what amplitude of vibration we're going to be obtained by substituting these two parameters into the simulation. So I'm going to be doing that by calling the cproc command, the compile procedure, and I'm going to pass these two parameters in order to calculate 6 the amplitude of vibration. So this is the damping coefficients. Okay, so let's run the simulation now, and let's plot the results and see how it looks like. Okay, so if you look at the result right now, you can see that the amplitude of vibration has been greatly reduced compared to the previous results. Okay, so through this simple problem, you can see that how Maple Optimization Toolbox can help solving optimization problems for a virtual model built in MapleSim. In the next example, I'm going to show a little bit more complex example. And the example that I want to show next is I want to use Maple Global Optimization Toolbox to identify the parameters for a lithium-ion battery model. So this is so what you see on the screen right now is the model of a lithium-ion battery. This is a very high fidelity lithium-ion battery, and a lot of our users in the automotive industry or handheld devices request for this battery model as part of their and then make it part of their physical system. But one of the questions that I usually receive from the MapleSim user who are using my battery model is that how are we gonna identify the physical parameters for this battery model so that it behaves the same as the battery systems that they have. So you can see that if you look over here on the right hand side, you can see this is a list of battery parameters, and for example, AP, AN, AS are corresponding to the area of cathode, anode, and separator on the lithium ion cell. We also have the other parameters like the thicknesses of electrode and the other electrochemical parameters as well. So how are we gonna identify these parameters so that the simulation results match up with the experiment data? So let's assume that so this is a model that I set up in MapleSim for parameter identification purposes. In order to identify the parameters, we first need to get the measurements from an actual battery. So I have obtained a different sets of measurement data for lithium ion cells, and I have attached this data sets to the lithium ion battery models, and this data set can be seen under the attachment palette on the left hand side here. For example, let me open one of them. So, and this data set will actually enter in Excel spreadsheet. So, and you can see here, so the first column is corresponding to the discharge time, the second column is the discharge current, and the last column is the battery voltage, which go from 4.1 volt when the battery is full to 2.5 when the battery is fully depleted. So this is the voltage curve versus the discharge time using a constant current 1.194. Okay, so once we have this set of test data, what we can do is that we can use the global optimization toolbox in Maple to identify the set of parameters for this battery. In order to save time, I actually prepare some Maple commands here, and I'm not gonna be typing any command. I'm just explain what this command does do in this Maple worksheet. So similarly, what you see, the first command is to link the MapleSim model for a lithium-ion battery to the variable A. And the next command, I am calling the get attachment command in the MapleSim API package to extract the attachment, the Excel attachment. So if let me execute this command so you can see the results. Okay, and you can click on the results returned by this command. You're going to see exactly the same set of data that you just have seen in the Excel spreadsheet. You're going to see the 3 columns for time, discharge current, and battery voltage. And the next 2 commands, I want to extract, I want to separate the time vector and the voltage vector, which are the 2 vectors that I need for the parameter identification process. So I just ran these 2 commands to extract the time column that you can see here and the voltage column. Okay. And what I want to do next is I want to define the list of parameters that I want to identify. So there are a lot of parameters in this battery model. In order to identify all the parameters, it will take the algorithms a fair amount of time to run. In this simple example, I'm defining only 4 parameters. And these are some of the key parameters that I want to identify. So the first one is the area of the electrode. The next 3 parameters are the thicknesses of the cathode, separator, and anode on the lithium-ion cell. And I'm using some default parameters as well, so that I can simulate the compiled C code after I call the get compile procedure command in the Maple API, in the MapleSim API package. So the next command, again, I'm calling the getCompileProc command using the Rosenbrock solver. The reason why I'm using a Rosenbrock solver here because the battery model is a very stiff model and it needs a very robust solver to solve it. I'm also using the sampling rate of 1 second, and I will pass the list of parameters that I have defined before into this getCompileProc command, and I will generate a C code by calling this. It will take a few seconds because this is a very large model. The battery model contains hundreds of equations, and it takes a little while to generate a C code out of that. Okay, so it's completed. And the next step is to define the objective function. So this is procedures that I have seen in the tune mass damper system examples that I have shown you. So the objective functions that I'm defining here is actually very similar to what you have seen. I'm passing the two parameters a, lp, ls, and ln into this procedure. I also run the simulation by calling the compiled procedure and pass these 4 parameters into this compiled procedure. And once I obtain the simulation results, I will calculate the what I call the weighted least square error. And so there are 2 ways that I'm using here. The first one is for the battery voltage, and the second one is for the simulation time. So the reason why I'm using the simulation time here because I want the virtual model in MapleSim to become fully discharged at exactly the same time as the real life battery system. So this is a very crucial for battery the parameter identification, because this indicates that the virtual model and the actual battery have the same capacity. So I'm just need to execute this objective function now. And the command that I'm using here is the global solve command in the global optimization toolbox, and I'm passing the objective function with the 4 parameters a, lp, ls, and ln into this command. And I'm using the method differential evolution. I'm also defining a time limit here because I don't want the computation to take too long, so I'm just running this computation for 10 seconds. And I will want to minimize the object function so that the simulation results match with the experiment data. And I'm also defining the option evaluation limit here, and also the objective target of 28. So the computation will stop when any of this condition is met. So either the time is up, or the number of evaluation exceeds this number, or the objective or the value of the objective function is below this value. And for the contrary to the local optimization toolbox, for the global optimization toolbox, you will have to define a search range for each parameter. So from my experience, I know that by looking at the experiment data, I know that the area of electrode would go between 0.02 to 0.9, and the thickness of electrodes usually between these numbers, between these ranges. So with all the options and parameters defined, I can then execute this command, and then just wait to get the optimal results. So it will take about 10 seconds to complete the computation. So now we have obtained the optimal solution, and the value of the objective function, the final value is roughly 51.3, which is higher than the objective target because the computational time is up already, so it will not take longer than that. And these are the set of optimal parameters, desired parameters that we have identified. So we have A equal to 0.13, and this is ln, lp, and ls. So what we want to do next is that we want to substitute this set of parameters into the MapleSim model and then simulate it. So if we run the simulation now, you can see that so this plot shows the voltage from the estimate voltage and the voltage coming from the experiment data. So you can see that the two batteries, the virtual model and the actual battery, behaves very similarly, and we have pretty good match between experiment data and simulation results. So we can improve this further by letting the computation run longer, or by using a larger set of parameters for the optimization process. And this is what I have done actually. For example, in Maple, you can use the embedded component in Maple to develop a template like this. So this is the battery parameter templates that I have developed, and it's actually based on the same algorithm. So this is I developed a fancy interface for that which allows the user to use it easier. So from here you can select the data sets that you want to use, and I have 4 different data sets here. So the more data sets you use, the more accurate the results you will get. And and if you scroll down, you can also select different parameters that I want to identify. So here I have select 1, 2, 3, 4, 5, 6, 7, 8, 9, about 8 parameters that I want to identify. So with those set of 8 parameters, I can have very accurate results.